All right. Section 2.8 is on related rates. So what this is a much better applications, real-world applications of implicit differentiation. So remember, with implicit differentiation, we said the derivative of y was y prime, but we did say the derivative of x was x prime. And remember, that was only because we were taking the derivative with respect to x. Well, here what we're able to do is we're going to start being able to compare things with time. In real world, we usually take things with how are they changing with respect to time. So now y is going to be a function of time implicitly, and x is also a function of time implicitly. So when we take the derivative of these equations, we're going to be taking them with respect to t, not with respect to x. So now when you take the derivative of y cubed, it's still 3y squared y prime, just like it was in the previous section. But now when you take the derivative of x cubed, it's going to be 3x squared x prime. Okay? So now you need the primes with both the x's and the y's. Because the variables don't match, you are taking the derivative with respect to t of everything. Other than that, everything's just the same. You're going to start off with an equation. You're going to take the derivative of both sides, but except now you don't necessarily solve for y prime. You might be solving for x prime. Heck, you might even be solving for x or y. But you're going to have a bunch of given information in the problem. Find the derivative of both sides, and then plug in that given information, and you'll be able to solve for exactly what you want. So nice real-world problems here, nice applications of implicit differentiation. So it says in the previous section, we looked at implicit functions. We said y is a function of x. Thus, we concluded that the derivative of y was y prime. And remember, we use y prime, not dy dx, okay? It says in this section, we'll think that every variable is an implicit function. So not just y's, also x's. It says, for instance, we can think both x and y are functions of time. So we would have the derivative of y and x are y prime and x prime, respectively. We want to make sure to use the chain rule when appropriate. For instance, suppose that x and y are related by the equation y equals 2x. If both variables are changing with respect to time, then their rates of change would also be related. So in other words, take the derivative with respect to t of both sides of the equation. So if we have y equals 2x and we take the derivative with respect to t of both sides of this equation, because the variables don't match, the derivative of y is y prime. The derivative of 2x again would be 2x prime. And that's what they have written right there, except again they're using dy dt's and they're using dx dt's. I use the y primes and the x primes just because that's the notation I prefer. Example 1 says examining two rates that are related. The variables x and y are differentiable function of t and are related by the equation y equals x cubed plus 2 when x equals 1, dx dt, which again I call x prime, is 3. It asks us to find dy dt when x equals 1. So what are we going to do here? Well, the first thing we're going to do is look at the equation. The original equation they gave us is y equals, and then we have x cubed plus 2. What we're going to do is we're going to realize both of these are now functions of t, so we're going to take the derivative of both sides of the equation with respect to t. When we do that, again, the derivative of y, like it has been, is y prime. Be careful with the derivative of x cubed. Now that would be 3x squared like it was, but remember we have to tack on the x prime. And the derivative of 2 is 0, so this is our derivative function. So this is how the rates are related. Now what we do is we look at the given information. It seems to me they give us x equals 1. Well, I would literally plug in where I see an x, I'd plug in 1. And it also gives me that x prime is equal to 3. So where I see an x prime, I'm going to plug in a 3. And that allows us to solve for dy dt, which is what they asked for, y prime, by plugging in those numbers. So we'd have y prime equals 3 times, instead of x, we know x is 1 squared. And then we know that x prime is a 3, so multiply that times 3. 3 times 1 squared times 3 would be 9. So dy dt would be 9. Again, we don't have units on this problem. It's not a real world problem, so we don't need to label this. But that's it. That's all you would do. Take the equation. Once you have the equation, take the derivative of both sides, plug in the given information, solve for what they want. So it says in example 1, you were given the mathematical model, in other words, the equation y equals x cubed plus 2. You were also given x prime is 3, and you were also given x equals 1. And it asked you to find dy dt. It says in the next examples, you must create the mathematical model from the verbal description. So in other words, what they're saying is they're not necessarily going to give you this equation. So there's definitely some equations that I expect you to remember. Those equations are written on the next page. So let's take a look at the next page in an overview. What types of things am I expecting you to memorize? Things like area of a circle. How do you find revenue, or more so profit? Okay, all those types of things.